Alrighty. First off, because of the snow day this week, no annual this week. So Friday we're just going to continue going over stuff, and then at this point the plan is to have a test next Thursday to kind of finish out this chapter. If that's the case, then next Friday will be annual and we'll be okay. If you don't make it there or feel like you need an extra day or whatever, we can push the test back to Friday. But the plan is to try to get the test next Thursday. Yes?
When you say no annual for the rest of the semester, are you talking just this class? Or
That's just, yeah, that's for me, yeah. So every teacher can do it however they want for annual. Some may say you still do, you don't have it. I know I was talking with Mrs. Brennan. I think she's still planning on not doing Friday stuff. What's her planning? Well, I think Mrs. Howie's planning on doing it. So, so it just depends. So that's not it's a teacher by teacher thing. So anyway, at least for this week, when I say next rest of the semester, I'm just giving you a heads up that it could happen, but not necessarily for sure. It just depends how we roll out. The last week of the semester will be midterm, review and midterm. I don't think we're doing a special schedule for midterms and final kind of stuff. So we'll probably split it over 2 days for in here. Because remember, anybody that is in CCP, your midterm is 25% of your grade. So a quarter of your grade comes down to that final test, which is over everything you've done this semester. So, yes?
Where do you get all these strange stats from? How do they even get this information?
All of these notes I'm using now, they have strange stats on there. I got these from when we used to teach statistics from the University of Findlay. And the professor at the University of Findlay gave us all the notes that she used in her class. So a lot of these, the basis of them were from her notes. And then I tweaked them over the years, and so but I kept the strange stats. So almost all of them were hers. So
I just want to understand who's asking 4-year-olds these questions.
So the average 4-year-old asks over 400 questions a day. If you've been around 4-year-olds, I would say that's low.
Why?
Yeah. Because how many times does a 4-year-old say, "Well, why?
Yeah, and who's recording that?
Why? Right. So somebody's doing that. Somebody's doing that research, recording that. You know, some sociologist, psychologist, child psychologist is doing it in college, figuring that out. So, all right. We are in here today till 11:18 for third period here, so we got a little over 20 minutes here. And when we looked at last week, we looked at probability distributions. And the things that we looked at, I want to refresh your memory about, was when we had our probability distributions, we had our random variable. Do you remember what a random variable was? We look at something like this. Right? And we had our random variable. Did something like that. So our random variable was the x. Those are the numerical values that can happen. Remember, the random variable has to be a number, a numerical thing. It can't be heads or tails. We have to keep track of the number of heads that I get. P of x is our probability. If we remembered what our probability always had to add up to 1. So if they didn't add up to 1, it wasn't a probability distribution. Okay. And then we talked about finding the mean and standard deviation of a probability distribution. You could do that on the calculator by typing into L1, L2 and doing one variable stats. Or, for those of you on the homework, if you didn't have a TI calculator with you at home, you could just take x times the P of x, add all those up, and that would be your mean. That would be your expected value, right? And we did a lot at the last section or two of finding that expected value. We spent a lot of time talking about casino games, and hopefully you watched all the videos and now you're all ready to go to Vegas when you hit 18 and know how to gamble on all those. Pretty much the moral of all those was what? Don't gamble. You're going to lose money, right? So no matter what you do, you're going to probably end up losing money because the expected value is going to end up being negative. Okay? So that was a general probability distribution. Today, we want to look at a specific type of probability distribution. And this one is a very important one. One of the charts in your formula sheet will be this binomial distribution. We're not going to get there today because of the shortened time. We're going to get to that tomorrow. Today, we want to mainly talk about what is the binomial probability distribution. Now, you've learned a little bit about binomial when we talk polynomials in algebra, right? You get a binomial, and the bi in front means 2. So we're going to have 4 characteristics of a binomial experiment or a binomial probability distribution. And if you're going to look at the rest of this entire year, after we get into the next semester, almost everything we do falls into 2 categories. We talked about, remember, discrete and continuous random variables. Continuous random variables come from things that are like, you measure a height, you measure weight, you measure time. You're measuring things, you get decimal points, right? You find means, standard deviations, some of those kind of things. The other half of what we're going to look at are things that are binomial. You have 2 outcomes. And that's one of our first, it's our second one, thing of a binomial is every trial has exactly 2 outcomes. And that's the most important. You don't have to write that whole paragraph necessarily. But everything comes down to success or failure. 2 outcomes. Pass, fail, true, false, yes, no. So anytime you're asking somebody like a survey question, you know, do you believe in Santa Claus? Yes, no. That's a binomial experiment. There's 2 outcomes. Right? And we're going to define these 2 outcomes as success and failure. And that can determine, you know, if you're a hunter and you went hunting the past week and shot at a deer, if you miss, is that success or failure? Unless you're the deer. And then from the deer's perspective, that was a success, right? So a lot of these, well, success and failure, it depends on what side of it you're on, right? If it's a game and somebody's at the foul line at the end of the game and they miss the shot and lose, if you're on the other team, that's a success. The team that missed, that's a failure. So sometimes it's going to depend on which side are you on. It's just going to change your probability. If I am out hunting and there's a 70% chance that if I shoot, I hit the deer, my probability of success would be 70. My probability of failure would be 30. From the deer's perspective, his probability of success is 30, and his probability of failure is 70. So sometimes it just depends which side of it you're on, but we do all of the statistical stuff is the same. You just have to define what do you mean by success and failure. Usually it'll be spelled out in the problem that we're talking about. All right, so our first one, 2 outcomes. That is why it's called binomial, 2 outcomes. Or it can be reduced to 2 outcomes. So you can reduce it to yes or no, pass, fail kind of stuff. All right, our first one. This is the other big one. A fixed number of trials. And all the trials need to be independent. But the bigger part of that is a fixed number. If you want to write it really simple, a fixed number of independent trials. There we go. I could have worded it like that and made it even shorter. A fixed number of independent trials. And I got the hunting analogy in my head, so I'm going to keep rolling with it. We got a question later about a sharpshooter shooting at a target, same idea. But here's the difference. This is not binomial. This is something we'll talk about next week. It's called geometric. It's a different type of probability distribution. Imagine you're shooting at a target. And I say you're going to shoot at that target 5 times. Fixed number of trials, right? How many times do you hit? 5 trials, you hit or you miss. Yes or no, 2 outcomes. That's different than there's a deer running and I'm going to fire at it, and I got to fire repeatedly, and on the fifth one I finally hit it. That's a different type of probability, because you don't know how many times, how many trials there are. It's how many trials until you get a hit. That's different than a fixed number of trials. I'm going to fire 5 times. Okay. All right. Number 3, the probability of success must remain the same for each trial. The probability doesn't change trial to trial. Now, we're going to kind of assume something like, if you're shooting at a target, are those truly independent? Does my last shot influence my next? Maybe a little bit. You know, if I'm at the foul line and I'm shooting in a basketball game and I got to make 2, I got to make at least 1, and I miss the first, does that change the probability I make the second because of all the psychological and all that kind of? Yeah, probably. We're not going to get into that too much. We're going to assume your probability of success doesn't change. We're going to assume the trials are kind of independent unless it specifically says otherwise. And then our last one, our X, our random variable, will always count the number of successes. So let's look at some examples here. And we want to go through each one and say, is this a binomial experiment? Is this a binomial situation or not? We survey 100 people to determine if they like sudsy soap. Fixed number of trials? Is there 2 outcomes? Yep. Independent, probability change. Those are kind of the 4 that we have up there. Fixed number, fixed, independent, 2 outcomes. Probability doesn't change, so that's yes. Okay. Because what we're assuming is there's some probability of people that like it. And we're just randomly asking 100 people. We're not saying, you know, it's not like everybody hears everybody else's answer to whatever. Draw a card from a deck. Getting a heart. Which one is not? If it's not binomial, which one's the problem? What's that?
The probability for its height, partner number.
No, yeah, you're right. I was just not thinking my own.
Oh, I'm sorry. I was like.
Okay, so we have 2 outcomes. Let's go through them. Is there 2 outcomes?
Yes.
Heart, no heart. Good. Is there a fixed number of trials?
No.
How many cards are they drawing?
1.
1. It's a fixed number of trials. 1. It's only 1 trial. Is it independent? And the probability not change? That's yes. What if I said drawing 3 cards and they're hearts?
No, that's enough.
Because the probability would change for each after you drew 1, right? And it'd be dependent, however you want to say it. Probability changes or the dependent, same similar idea. All right, asking 1,000 people which brand of cigarettes that they smoke. That's no, because more than 2 outcomes. However many brand of cigarettes there are. Test a brand of aspirin by using 10 people to determine whether it is effective.
I'd say
Why?
placebo.
What's that?
The placebo effect.
Okay, it's possible. So I understand your question. Your question is, how do we mathematically define effective? Right? Is that what you're thinking?
Yeah.
And what do you think? You said yes.
Yeah. Because matches all four.
What's that?
It passes all four of the tests.
So it meets all the things. The question of what does effective mean, right? We don't care. We're the statistician, we're the mathematician, we're looking at this as binomial distribution. We're not the ones setting what it means to be effective. That's determined by somebody, it's effective. So for us, that's a yes, because we're not trying to figure out what does effective mean. Because that's the really hard, complicated part, and we're going to say, we have some rule that we can use to say, yes, it's effective or not. So is it effective or not effective? Those are our two outcomes. What that level is not our concern. Asking 100 people if they smoke. Yes. And what is the difference between D and F? If you just ask them, do you smoke? That's different than which brand. Okay. Checking 1,000 applicants to see whether they are admitted to the University of Findlay.
Yes.
Yes, you can see this comes from Findlay. I didn't change the college there. Survey 300 prisoners to see how many different crimes they are convicted of. Why? More than two. Surveying 300 prisoners to see whether this is their first offense. Yeah. So you're looking at, okay, is there a fixed number? That's independent, probably doesn't change. And then you're trying to decide, is it a yes, no, pass, fail kind of question? Smoke, don't smoke. First offense, not first offense. Tossing a coin, yes. Did we skip that one?
I think so. Yes, we did. You put.
Oh.
You just went right to drawing cards.
Tossing a coin 100 times to see how many heads occur? Yes. You're counting the number of heads or tails, and two outcomes. All right, subnotation. P is our probability of success. Q is our probability of failure. Okay. N is the number of trials, and X is our number of successes. Now, whether it's P or Q kind of descends on the problem and what side of that coin are you on, right? Are you the hunter or are you the deer? That's going to change your probability of success or failure. And usually the problem spells that out, how you're doing, okay? All right. It really doesn't matter if you do it one way or the other. It just changes what the probabilities are. One's 30, one's 70, and they switch, and the chances of success or failure still works out, okay? All right. So we're going to kind of build this up a little bit, and then we're going to get to the formula, and that might be on the further we get today. So sharpshooter takes 3 shots at the target. She normally hits the target 70% of the time. Find the probability she hits the target exactly 2 times. Now, this is binomial. We're going to have a shortcut way to solve this here by the time we're done. But for now, you know how to do this from what we did in chapter 3. Do you remember what we did in chapter 3? We had a test over chapter 3. Do you remember what we were doing? Treating. It's been a long week, right? You could do a tree diagram. That'd be one option. I think that was going to be more complicated. So, you shoot at a target 3 times. What can happen? Hit or miss. So what happens the first time? Right? So you shoot the first time. You hit it. Okay, so the first time's a hit. What's the second time? Miss. And the third time? Hit. So there is, in 3 shots, it hit it exactly 2 times. What's the probability of getting a hit and a miss and a hit? How do you find the probability when you have this and this and then this happen? What's the probability of drawing a 2 and then drawing another 2 and then drawing a 10? What do you do with your probabilities? Multiply. So what's the probability of a hit? 70%. The miss? is 30, and the hit is 70. So the probability of that happening, we just take our calculator, 0.7 times 0.3 times 0.7, 0.147. But remember, when you calculate probabilities, the order matters. So if I missed and then hit and then hit, that would also work. What would that probability be? It'd be the same thing. What's another way it could occur? Hit, hit, miss. Is there another way to get 3 shots, 2 hits, and a miss? No. So if I take these 3 and I add them together, or take that one, I get 0.44. Nothing in there that we haven't done already that you should understand. Right? Now, depending, it's been a long time since we did that. That was before last week. That was before we even, week before last week. So it's been a while since we've done that. So you may not remember how to do that exactly by yourself. But there's nothing up there that surprises us, right? What if they shoot 8 times and hit exactly 6? Why do you say no? What's the problem? There's a lot of different ways, right? Okay. If you remember here, how many different, we wrote down the 3 that are possible, but how many total are there? It would be 2 times 2 times 2, so there'd be 8 different ways it could happen total. And these are the only 3 where you have exactly 2 hits. So if we're looking at 8, that would be 2 times 4, 8, 16, 32, 64, 128, 256 different ways you can shoot at the target, right? Think about, we're not doing that with a tree diagram, right? It'd be crazy. We could eventually get there if we wrote this too hard. So instead, we're going to look at this with a formula. So here is our formula. This is our probability of X successes is n factorial over n minus X factorial divided by X factorial. The P of X to the Q n minus X. Or you can see it down there that this is just n C X times P of X times Q minus X. And if you want the English explanation, what does the NCX mean? What did we do that in the last chapter? That was our way of combination. So effectively what's happening is, if you go back here, what this formula is doing this. It's taking our probability of successes times our failures, and then that combination part is determining the number of ways it can happen. So let's use our formula here. Our n here is 3. Our x is 2. Our p is 0.7, and our q is 0.3. Yeah.
Is there any particular reason why every single X is an R on our paper?
Does it show an R on yours?
Yeah.
All right, I gotta fix that. Our old textbook used R instead of X. So our probability of X here, or in this case we're doing 2, would be 3C2 0.7 squared times 0.3 to the first. Can you look at the formula and see how I got that?
Yes.
And notice what that is doing over here. Over here, we had 0.7 times 0.7 times 0.3. That is that part, right? And then if we do the combination of 3 choose 2, watch what we get on our calculator. 3. What do you think that's going to be? That, from this example,
Or 0.147. 3.
it's going to be the number of ways this could occur.
Oh.
So that is 3. Now, the second part of it is this 0.7 squared times 0.3. That's going to be our 0.17. So we take that 3 times 0.7 squared times 0.3. Let me get to it. So the way this formula works is the NCX or NCR part in the front is the number of ways it can occur. Then this part of it, the second half of it, is your successes and failures. Okay. So, real quick in the time we got left, how would you do this one? Our N is 8, our X is 6, our P is still 0.7, and our Q is 0.3. So our probability of 6, 8 C6, 0.7, 6, 0.3, 2. See if you can type that into the calculator. See what you get. I get 0.9, let's say 6.5 or 6.47, right there if you go 3 quarters. Tomorrow we'll show you how you can do this without using the formula. You're going to have a chart in your formula sheet. You can just look that up and go, there's the